Hello and welcome in another episode of my tutorial series on STM32 programming. This time I would like to show you a proper way how to debounce a push button. At first I will talk about the problem itself, then I will show you a hardware ways of debouncing, and in the end I will show you a software way of debouncing the button. So here you can see two proper examples of bouncing. On the left you can see pull-up switch or button, which if pressed starts to bounce before finally stabilize itself on a logical 0 value. And on the right you can either see a pull down switch or if a behavior of a button if you are depressing the button, because even if you are depressing the button, during depressing you can bounce between logical 1 and 0. So the first way to fix this problem is by using a hardware, and such a way is, for example, using a simple RC circuit, but it usually doesn't help that much, because what it does, I will show you over here, it smoothens the rise and fall, smoothens the rising and falling edge, right? And therefore it doesn't bounce, but the that time basically between 1 and 0 is long. But this is not a proper way how to toggle between 1 and 0. Between 1 and 0 you must toggle as fast as possible, which is this green line. This is a proper toggle between 1 and 0, and the yellow is the voltage basically on your input pin. But we can eliminate this behavior also by adding a Schmidt trigger integrated circuit, which is over here. Over here this is a hysteresis sign, and this is the name, for example, of one of the integrated circuits which contains these Schmidt triggers. The only negative way it does is that it not inverts the signal basically, but you can fix it that if you want to trigger, for example, external interrupt on falling edge, and here you have a pull-up button or pull-up switch in this case, that you will put two these blocks in series. Therefore you will have 0, 1 and 0. But why don't we use hardware debouncing all the time? Well, it can get quite expensive, especially if you have multiple switches or buttons, and at first it takes a lot of place on your PCB, and as I said before, as a second, it can get quite expensive. Even though like one capacitor, one resistor, and even these Schmidt triggers are not that expensive, the price will add up, and eventually it is cheaper to debounce in a software. The downside of debouncing inside the software is that the program takes some of the memory and some of the clock cycles. Now we can see the flowchart of the debouncing program. On the left we can see an external interrupt routines, for example for channel 3 and channel 9 to 5, depends where your button is, on which pins your button is connected to. And the only thing we do inside this interrupt routine is that we set the flag variable to 1. Then we just clear the pending register, which we have to do, and we go back to our while loop. Then on the right we have sysdig handler interrupt routine. This why I use sysdig handler? You can use even a general timer if you want to, and you can just set some ticks, and on end of each period you will have a callback interrupt, and you can do this also. But I'm using sysdig handler because if you programming STM32 microcontrollers and you are using a hardware abstraction layer which is provided by ST, every time you initialize your program or generate your code from the Cube IDE or CubeMX, it initializes the sysdig timer because you have to use it for a HAL delay function. So I do not initialize another timer since this one is already in function and I'm not using real-time operating system. So every millisecond, for example, if you have sysdig configured on 1 millisecond to trigger an interrupt, we have a variable y equal to 0. We set it to 0. And then we go to first condition. I is smaller than number of buttons. Let's say I have 2 buttons. 0 is smaller than 2. That's true. Now, flag variable. I didn't mention flag variable is actually array of elements, the number of elements are the number of buttons. So you have 2 buttons, therefore this array have 2 elements. And we are now accessing the first element of this array. Is it equal to 1? Let's say we haven't pressed any of the buttons. No, it's not equal to 1, it's false. We increment y by 1. Again, we go to this condition. Again, it's true, 1 is smaller than 2. Then, again, flag variable is equal to 0. We increase the y variable. Now this condition is not true because 2 is not smaller than 2. It's false, and we go back to our while loop. This is the downside of software debouncing, that even though you are not pressing the button, I'm still constantly checking by this timer if the button has been pressed, and it takes some of the clock cycle. It is not much because it happens in 1 millisecond, and this can eat, for example, like less than 30 clock cycles, 20 clock cycles, I don't know right now. So this is one of the downsides, but it is still I think the most efficient way how to debounce the button, because many people are using just simple delays, and or they are using the timer just in wrong way, basically. Now let's move into another case when we press one button, for example. It will be the first button, which means the 0 element of the array. Y is equal to 0. Yes, it's true. Now this condition is true. Now x, y is smaller than number of checks. This is the number of checks. Basically, you can transfer as the time or the duration of the checking of the debouncing of the button. For now, let's say I want to check the button for 50 milliseconds, which means that I have to enter this interrupt 50 times to find out if I press the button or not. If it's just some sort of noise or electromagnetic interference and stuff like that. So at first, this statement is true. Because x, I didn't mention, x is initialized on 0. I increment x, and right now, is pin low. This time, we have to read the pin if the voltage, if there is any voltage on the pin, which means it's 1, or if it's pressed and it's 0. Let's say it's true. Then we have another variable. It is called, for example, low state variable. Again, it's an array dependent on the number of buttons. And for this case, the button is pressed, so I increment it. Now let's go all the way to the beginning. Y equal plus plus. Now I'm checking the second button, which is depressed. I escape the interrupt. Then again, I enter this handler. For first button, it's true. I go all the way over here and again. And this block basically repeats itself 50 times for one button. And this condition, for example, from 50 cycles, only 45 times this statement is true because of the bouncing. For example, 5 times actually the pin thinks it is not pressed, so because there is some bouncing voltage. So after 50 cycles, this condition will be false. Now, low state variable is larger than desired confidence threshold value. Let's say I check this button for 50 milliseconds and I want this button to be pressed at least for 30 milliseconds. If 30 times out of 50 there is no voltage on the pin, I can safely say the button has been pressed. Therefore, if it's true, do whatever you want to do, the function or set something up by pressing the button. If it's false, you will just do nothing, skip to this block. And in this block, we are just setting flag variable back to 0, low state variable back to 0, and X variable for this. Everything is array and everything is just for this button. And we are going back and we are checking another switch. You can press 2 buttons at once and it can check 2 buttons simultaneously. This is the upside of this program. So here is the flowchart, and now let's go to Cube IDE to show you how to do it inside the code. At first, I will just show you how I have my MCU initialized. Inside clock, I have 48 megahertz. This is only thing I set up. Everything is default. Right now, I have 2 LED pins, LED1, LED2, and 2 button pins, PB3 and PB5. I'm using STM32 F303 on a Nucleo board, Nucleo 64 board. And I initialize the button pins as GPIO external interrupt, this case channel 3 and this case channel 5. These 4 pins are only for initializing the timer. As you can see, it is orange because I set it up as the timer channels, but I haven't initialized the timer. I initialize it. Oh, something happened. It's okay, I hope. I initialized it only as GPIOs. I want to initialize the timer by myself because I found it easier to do it than using this IDE, because this is not as accessible as to write each register by yourself. Then inside GPIO, you go inside your buttons, and here you can see external interrupt mode. By default, it's on rising edge. You have to set it up on falling edge trigger detection if you are using a pull-up button. Over here on this button also. And you can see you have GPIO pull-up, pull-down. In this case, I have it no pull-up, no pull-down. And on this case, I have it pull-up. This is basically the internal resistor. The MCU on the GPIO peripheral has some internal resistors, and you can set it up internally if you want pull up and pull down. In this case, I set it up, and in other case I have not. I just did it to show you that you can use external resistors, and this internal resistor at the same time it will work just fine if you accidentally switch it on. Then in nested vector interrupt controller, you enable both these interrupt channels, interrupt vectors, line 3 and line 9 to 5. You can do it also over here. Here are all the interrupt vectors. So I think this is all inside CubeMX. You will press generate the code. I already generated the code, so I will go to the main.c. And let's go from top to bottom. Over here I have the variable, the button flag. You could see it on the flowchart. Then I have a button press counter again on the flowchart. X variable, which is basically the number of the currently running test. And then I have some support variables y and n. This rest of it, this is only for showcasing of the function of buttons. This is for the timer, but this is not part of this tutorial. Watch my PWM generation tutorial. Next, you have to do sysdig config to make sure that the sysdig handler runs an interrupt every millisecond. You have to set sysdig config over here with your clock frequency, which is 48 megahertz in my case, divided by 1000 to get millisecond interrupts. This is just timer setup. Let's not talk about it. And let's go into interrupt requests handler. Over here in this case, if button flag is 0, set it to 1. And if it's already 1, if you press the button again, don't set it to 1, just like that. And over here for the second button, to get this interrupt handlers, you can also go to STM32 in my case f3 it.c, and you can find it inside your source folder over here. It is in the same folder where your main is, and here you have all the handlers, interrupt handlers, and over here by default you have a sysdig timer, and beneath there you have peripheral interrupt handlers, which are generated by depending on your configuration inside CubeMX. I cut and paste them inside the main just to have the code inside one place. So this is like exactly the same. And now let's go inside our sysdig handler, which means if we press the button, here you can see for y initialized to 0, y is smaller than 2, y plus plus, the same as in the flowchart. If button flag, depending on the number of the button, is not equal 0, which means it is 1, in my case, let's go to another condition. If x for button 0, for example, is smaller than 50, which means we are checking the button for 50 milliseconds, x plus plus, and then we are switching case for y variable. For case 0, which is button 1, if then we read the pin, this is the another condition that we are reading the pin. If it's not set, which means it is reset state, button press counter plus plus, which is the which increments every time the button is depressed. Then we break out from the switch, from this case, and we go out. And over here, this is else. This is when this condition is false, but right now we are skipping it all the way out from the code. Let's say after 50 loops, after we entered this interrupt for 15th time, we skip this block and go inside else. And again, switch y. And for button 1, which is case 0, is the button press counter larger than 30, which means that 30 times out of 50, the button was depressed. We toggle a pin, which is, for example, what I want to do. I want to make the button do something if it was pressed. So I toggle the pin, and then, for example, I change the variable n++ for this condition, but this is for timer setup. And then, after I escape this if statement, I reset the button press counter to 0. I must do it if for this case and outside this if statement. Because if, for example, the button was not pressed, if it was just some sort of noise which triggered an interrupt, and there are only, this variable is only equal, for example, 2 out of 50, I will skip this statement and I must reset it. So next time I press the button again, I start from the 0. Then again, I escape this switch, this switch statement, and go inside button. Basically, I only reset the button flag. I click over here. I reset the button flag back to 0 for this button and X variable back to 0, and then I escape it. So this is all for the code. I think this is the most practical way how to debounce the button, and now I will record you how this program works in real life. Here you can see that the button also changes the frequency of the signal. I can press 2 buttons at the same time, which you cannot do if you are using just a simple delay. And you can see the frequency doesn't change. You can also use this function another way. You don't have to use it only for pressing the button, but if you want to press the button and hold it to do something, you can do it also. I can, for example, switch this. Let's say I want to hold the button at least for half a second to do some function. So I will do here on the top. I will change the number of tests, let's say on 600. And if from the 600 times 500, I can do it 550, let's say. 500 times the button is depressed. Then do some do something. So I run the code and I will show you the results for this scenario. And this is how it works. I press it shortly, it does nothing. If I hold it, it toggles. The only downside is that if you press the button and then you change your mind and you want to press it again, it will not toggle, because there is an ongoing process of determining if the button was pressed or not, and you have no chance of doing enough pulses which are showing that the button is depressed. Basically, yeah, now it doesn't toggle because right now there is an ongoing process of determining if the button is depressed. And if you, during that process, depress the button and change your mind and press it again, you have no chance of doing enough positive tests to toggle and button. So you must wait for half a second until this process is done. And now that's it. Thank you for watching this video. I hope you learned something useful today. If you like this video, press a like and share it with others. And see you next time. Goodbye.